in the University Navi Mumbai for giving me this opportunity to conduct sessions on quantum computing, quantum artificial intelligence. Quantum computing. So now we go back to how we can use quantum mechanics related properties, or which are the fundamental properties in quantum physics that are very crucial for quantum computers, building the hardware or applying the software. Okay, so let's just go through this. So the fundamental block of storing information in quantum computer is called as qubit. Okay, where two states 0 and 1 exist simultaneously in superposition, and unless and until you make something called as measurement, unless and until you measure, you will not know what it contains. Okay, so this is called as superposition property in quantum physics. There are certain new papers which talk about more than two states also getting superimposed. They are called as qubits, or 3 states or 4 states, etc. But we will not go there. It will again further complicate the mathematics. But the general acceptance is you have 2 states that are superimposed in the single most building block of quantum information, that is a qubit. Okay? And as opposed to a classical bit. In a classical bit, you either have a 0 or a 1 as a storage. Then in qubit, you have something called as here, there is something called as block sphere. In a complex domain, you have a unit sphere, because there is one axis 0 and one another axis 1. So all states of 0 and 1 superimposed lie on the surface of this sphere. Okay, so that is how it is mathematically represented. The analogy is like that. Okay. Some of the important things about quantum computing. Quantum computing measurement itself is inherently probabilistic, and the reason lies in quantum physics. So I will touch base with quantum physics, some of the principles, but you let me know if you want to go there, because quantum physics is governed by some of the very fascinating laws. Of course, it is a topic of interest for me. Heisenberg's uncertainty principle, for example. Right? So when we talk about superposition, it is also very important phenomenon which comes from these basic postulates in quantum theory. So the wave-particle duality of the nature of systems of particles at the atomic scales was studied in parallel during the era of Einstein by several scientists like Niels Bohr, then Heisenberg, and several others, Dirac, Paul and Dirac, etc. So some scientists gave the wave equation, etc. So, but I think everyone must know some of the basics of quantum physics in order to move towards quantum computing, at least at some fundamental level. Okay, so you have something called as nature of a particular particle. Let's say I have grains of let's say some grain. Let's say गेहूं का दाना लीजिए, मोहरी का दाना, ajwain, whatever. And if you have lot of such particles, if I bombard them, okay, then let's assume that there is a hole. the systems that are in practice have not been used so far to develop computational devices. So to give a glimpse, I will just move to this slide first, which talks about what are different systems there in use for utilization of those systems to do computations. So how many of you are aware that mechanical systems can be used to do computations? So any idea if anyone can explain? Okay, so when we say mechanical systems, these are also called as analog computers, right? So Kelvin actually worked a lot on this idea, and yesterday only I was seeing this video, so on YouTube I will share the link also with you. So again, the analog computers are coming back into picture. There are both advantages and disadvantages of both digital and analog computers. So mechanical systems, when I say, for example, I have a pulley and I have some mechanism, I can do some calculations based on that. Especially on the Fourier domain, it is very useful. If I would, and this was first utilized during the Second World War to analyze and predict the sea waves, ocean waves, okay, because it was very important for the soldiers from both the sides, so the Allied forces as well as the Germany and others. So basically, they wanted to predict on the seashore there were systems installed so that invaders would not be able to invade, let's say, some of the countries, and then United States wanted to predict that how can we exactly predict the nature of tides so that we will come to a conclusion, and based on that we will have a defense strategy. So basically a strategy for during the World War for attacks. So the problem statement was prediction of tides, and this was a problem related to Fourier series and Fourier analysis, where they wanted to, because high tide, low tide, if you plot it, it is a combination of multiple sinusoidal frequencies. So if you are able to decompose and reconstruct the frequencies correctly, then you have solved that problem. And again, tides were considered to be a function of basically three parts, I think, related to the motion of Sun, Earth and Moon. And because we knew the precise positions of those, calculating the exact function that used to that every tide followed was possible, and if we were able to do that precisely, then that was used for a different purpose. But it went a lot into analog computers. The analog computers were in use till 1960, and we also had electrical computers, right? So these diodes and other devices were used. So the device that we are seeing today here, this laptop or this phone, so it is the analog devices on mechanical side, or maybe it was impossible to construct a device which can do computations similar to this one using mechanical engineering systems. Similarly, on electrical side, the diodes and triodes were very huge. So a small computer would occupy the whole building, this much of size of electrical computer. Then with the advent of electronics, and this is where actually the revolution began. When we started, and there were some papers from Shannon, and so the famous Shannon and Nichols theorem, which talks about the limitation on sampling frequency. So there were people like Turing and then Shannon, based on the research of these guys, especially Turing did it for British government, to decode the signals during the Second World War for German whatever radio frequencies, they were able to decode it. And that was the first application of digital computer that was used. And especially these guys showed, I think Shannon, that you can decompose every problem by converting it into Boolean algebra. So you can convert each of the input signal by sampling it correctly based on the request frequency, and then accordingly you are able to decompose it into Boolean algebra. So if it is Boolean algebra, then we can use two states only, which is 0 and 1. So it was easier to maintain in an electronic system, and that is where they used to define let's say 0 to 5 volts or 0 to 10 volts. After a particular threshold, you will consider it as 1, or after below a particular threshold, you will consider it 0 or vice versa. So digital systems, when they started developing it, it also had an upper edge that it was always precise. It may happen that if a digital computer is there, if you use another digital computer, and if you use it multiple times, then it used to give you precise calculations, as opposed to analog computer. In analog computer, because it was a mechanical device, it was not possible for you to provide the same input every time, because the input was more or less continuous nature, because it was the movement of the pulley or something related to a mechanical system. So you can't guarantee that whatever input went into the calculating machine was the same. So to give you a gist of it, I think I will share the YouTube videos. You should go to them. It will be much more helpful for you to understand. Apart from that, when digital electronics came into picture, it revolutionized the whole story, because we had large-scale integration and then very large-scale integration, which is today also driving the whole industry. All classical computers today developed are based on electronics only, where we were able to fabricate more and more complex circuitry into smaller and smaller size. Okay, the spatial dimensions. So chip fabrication was one of the key to accelerate the development of and manufacturing of electronic computers, and the use of these electronic computers was getting multifold with Moore's law. How many of you know Moore's law? I think most of the faculties must be knowing, right? So Moore predicted that after every couple of years or a year, you will get more number of bits, as well as the CPU performance, as well as the memory. Both will be doubled each year or after 2 years. Something. There is a steep curve like this. So, and it worked. Why it worked? Because from electronic systems perspective, whatever mechanism we used to develop the electronic circuitry, it was possible for us to go to VLSI integration and have smaller and smaller and smaller chips, more and more complex circuitry. So we can do more and more complex calculations, and also develop CPU, central processing units, or the respective processors that can do computations faster. So both from registers and the manufacturing of all these things, we went into an era where there was a lot of high performing central processing units and memories getting manufactured. Every year or two, we used to get a better chip, and then manufacturing companies like Intel, AMD, they started doing this race that they manufactured better and better performance CPUs and better random access memory, etc. Then Moore's law started failing, right? So we know today that the reason we manufacture multi-core CPUs today is the parallelization in the computer software industry came because we had a limit on how can, in the same space, people were not able to manufacture a better central processing unit or a better RAM. So from that perspective, they thought that then we can actually have 2 CPUs, 2 cores, 4 cores, quadra-core, octa-core, right? That had different implications on the way programming was done, from a high-level programming language. And we faced an issue that from past 3-4 decades, it was very rare to find a generation of computer programmers who can implement parallel programs, right? So which can run, because the paradigm is different. It is not the same. the way you program on a single core processing unit. So in a similar fashion, because this started, and second, the main reason for it is that the dimensions in which we started manufacturing classical computing hardware using VLSI technologies actually hit a limit, and that limit was atom itself. Okay, so we ended up to, let's say, 100 atoms. Then if we go below 100 atoms, the laws of quantum mechanics start slowly creeping in. So in physics, there is a huge gap, okay, in our understanding of the universe. So there is something called as a small scale universe, for which we have very robust laws given by quantum mechanics. Okay, and they are a particular set of laws. And then on these scales, mesoscale and higher, basically, we have classical mechanics and then general relativity if you go to higher dimensions. So from the integration of these two has been always a problem. So multi-scale material modeling has always been heuristic, of heuristic nature, because that in between dimensions from a single atom or a couple of atoms or molecules to a level where classical mechanics starts obeying, or when you calculate Young's modulus, tensile strength, that is what we know from experimentation. But you can't derive Young's modulus as a function of the electromagnetic forces of atoms and molecules that make Young's modulus as the stress and strain for a material. So that has always been a problem in material science. So computational material science was always heuristic. People had various different ideas to implement at those scales. But because of Moore's law failing, the manufacturing companies like Intel, they hit the benchmark. They started developing multi-core GPUs and all. Then we had GPUs where NVIDIA and other industries started coming into picture, which we still have a very robust technology. But this idea, which came from Richard Feynman, it was very crucial in implementing certain type of systems for our use for doing calculations. And the analogy of an analog computer is very important to understand, because it is a type of system which we can see as a mechanical system, like a clock. Right? If there is a hand of a clock and you are using the hand of a clock or a watch to do some calculation, okay, I can attach some string or something, and then I can get a, because this is simple harmonic motion, right? So I can have a simple harmonic oscillator, even or a pendulum, and then let's say very close to simple harmonic motion, not angular SHL, but if you use it, you can simulate a sinusoidal wave of a particular frequency. So this is similar to understanding the analogy of an analog computer. And mechanical engineering systems, that is analog systems, used for doing calculations is very useful in understanding the analogy of quantum computers also. That's what I personally feel. Again, most of the people might not teach it that way. They will directly jump into quantum physics or quantum mechanics. But the whole point here is that whatever calculations we are trying to do, which type of system we have used to simulate it is very crucial in developing those machines. So then we come back now to quantum computing. So this is something which is the evolution, right? So supercomputing architectures we had, so multiple different types of distributed architectures, parallel architectures, Perm 10,000 and all we had ourselves developed in CRAN. And edge computers with Raspberry Pi-like devices, we were able to have our off-the-shelf operating systems mounted on edge node devices. So it was possible for us now, with the advent of Raspberry Pi, anybody can come who knows Python and run a program on Raspberry Pi. It was not possible earlier. Only those who know low-level C and Arduino programming can do those stuff and then have some specific device programming, either low-level C or some HDL, some VHDL related languages for chip fabrication, etc. used to do that. Then we had again hybrid classical computing architectures that you combine these things, cloud computing, mesh computing, and edge computing, etc. But all these things, given a choice that, let's say we have all these things, do we really need quantum computer? Is the main question, right? And why we should go towards it. So people started exploring questions like, are all problems solvable? Okay. Can you so let's say if there is a set of all problems in the world, okay, how many are solvable? So there is an MIT lecture, if you go and see on the open courseware of MIT on algorithms, there is a proof that this guy gives, which talks about that out of all the known and unknown, whatever existing problems, there are very few problems that we can actually solve. Okay, so this is very demotivating, but that is the truth. So mathematically, it is true. Okay. Then there are certain mathematics-related paradoxes of self-referentiality, self-referencing, and all, which also again in the same era, 1900 to 1940, 50, some of the mathematicians like Gödel and others, they invested a lot of time in finding out answers to problems. Hilbert was one of them, who always believed that no, everything is solvable, we can predict things. Okay, so can mathematics be certain, predictable, and there are these three actions? If you are proven wrong, no matter how much mathematics we use and put it to our implementation, it will not be always, we cannot be always certain. There will always be some use case for which it will not work. So, but again, this applies to every machine as well. Okay, so but in solving all these things, people started developing better and better technologies, and that is what this whole evolution is about. So when people started thinking about can quantum mechanics based systems be used to do computing, at that time, because Richard Feynman said that yes, this is also possible, there were different challenges for utilization of quantum mechanics based systems for performing computations. Okay, there are two things. If you want to understand quantum computing, you will need to have some glimpse of quantum physics. Then you will need to understand the underlying mathematics that is needed to do computer programming. Okay, so basically for quantum computers. And then once you understand that, then there is a whole new ballgame where you have multiple types of devices, and then how these devices can be put to use for solving a certain class of problems. So earlier people thought that quantum computers can only be used to have better performance of algorithms as compared to classical ones. But that is not the only case. I am working on quantum machine learning now for past several years. So some of the predominant players in quantum machine learning across the globe, the claim is that we still need to figure out the specific problems for which no classical supercomputer will be able to solve that problem. And this is the major problem in applications of quantum computing to business, especially today. Okay, in academia and R&D government institutions, there is huge amount of funding because of the potential that quantum computing industry possesses. Okay, because of some of the threats that it poses to existing systems. If it is a quantum cryptography for cyber security per se, where any Shor's algorithm is something which was in 1995 or 96 somewhere. Peter Shor, who got the Nobel Prize recently. So he is the one who developed an algorithm for prime factorization. So all our cryptographic SHA and other RSA cryptographic mechanisms today are based on that we cannot factor prime numbers. Okay, but if you give me a 1 million qubit quantum computer today, we have the algorithm, I will show it to you. You can easily crack any RSA encryption using Shor's algorithm. Okay, so that is the main threat. That's why banks are investing trillions of dollars, because the banks have always prevented their data. Banks will never put their data from on-premise clusters to cloud. Public cloud पे कभी नहीं जाएगा. It will never go there. because it is highly secured data. So now the security itself is at threat. So can we use quantum cryptography itself to prevent or create a barrier which cannot be broken by any quantum computer? Then a different family or set of algorithms people started discovering, which is called as quantum key distribution. It's a protocol based on which people started implementing quantum cryptography. Again, if you ask me today, we don't have the machines that can execute, even though we have algorithms, we don't have the machines where we can execute it on large data sets and crack the codes. But still, it is a threat, because if any of the players in the world or any government, anybody is successful in developing a large scale noiseless quantum computer, then it will be a big threat not only to banking and fintech but all different industries, space industry, defense, everybody. Okay, so security threat is one of the drivers for quantum. Then the AI community started thinking in that we can also use quantum for quantum machine learning. So quantum machine learning in itself is a big area. Okay, the algorithmic time complexity of quantum machine learning algorithms, you cannot calculate it the way we calculate it for classical machine learning. Okay, so there are fundamental things that are still yet debatable on quantum computing. Okay, but still there are novel ways getting discovered every now and then, because this is a very research-driven industry, and every day you will see lot many people across the globe, lot many researchers are participating, and novel techniques using different types of hardware and different types of algorithms, software are getting discovered, which might be useful to solve a particular specific type of problem. And that is where the importance of quantum computing comes into picture. That there are certain classes of problems which we thought we will be never able to solve at all, because for example, n-body simulations at an atomic scale. Okay, the behavior of materials at an atomic scale, it is governed by quantum mechanics. So an n-body problem is very complicated. You cannot solve it. Theoretically, you can prove that mathematically it is such a complex system. Even if you get a supercomputer, it is not possible for you to solve that problem. But if you use quantum mechanical system itself to simulate the behavior of a quantum material, then this is much more a solvable problem which can never be solved using classical supercomputers at all. So there are families of problems getting discovered every now and then, for which this type of machines, that is quantum computers, will be very useful. And again, we have to couple them with the existing classical computing devices in order to make them useful. Mostly, if you use both of them together, then typically it is called hybrid quantum classical algorithms or hybrid quantum classical systems. Then if you have a specific algorithm only implemented on quantum computer, it is quantum algorithm or quantum machine learning algorithm which will only run on independently on a quantum computer, which might have its own usefulness. Similarly, there is something that is quantum inspired machine learning algorithms, and we will cover different definitions of this. People are coming up with different terms that are getting coined. So like we cover these things, these are different types of ways in which we can develop a quantum computing hardware. Okay, so so there are a couple of things with broad class of rules that I have come up in the past 5 to 7 years, which I would like to share. For example, the algorithms in quantum computing, okay, are very tightly coupled most of the times with the hardware, underlying hardware. So it is not the case that you have an algorithm that will run on a superconducting qubits based quantum computer that will also run on a photonic quantum computer. Not necessarily. Okay, so some algorithms will run on photonic qubits based hardware. Analog computing devices will have different types of family of algorithms, etc. But still we have come up with some basic underlying mathematics, okay, which is a foundation of developing quantum computing programs and algorithms. Okay, so and because the initial most player was D-Wave, who developed quantum annealing based hardware. So D-Wave had today like close to 5,000 or even more than 5,000 qubit based quantum computer, which is based on something called as quantum annealing. Okay, so we will come to these different families of quantum computing hardware. But at this point, I just wanted to touch base with the history of why quantum computers. Okay, so it is not that quantum computers are going to replace all different types of supercomputers in this world, classical supercomputers or classical computing devices. It is not going to happen. Similarly, there are multiple areas like quantum sensing devices, etc., which have their own applications. But again, quantum computing. So now we will go back to how we can use quantum mechanics related properties, or which are the fundamental properties in quantum physics that are very crucial for quantum computers, building the hardware or applying the software. Okay, so let's just go through this. So the fundamental block of storing information in quantum computer is called as qubit. Okay, where two states 0 and 1 exist simultaneously in superposition, and unless and until you make something called as measurement, unless and until you measure, you will not know what it contains. Okay, so this is called as superposition. Okay, property in quantum physics. There are certain new papers which talk about some more than two states also getting superimposed. They are called as qubits, 3 states or 4 states, etc. But we will not go there. It will again further complicate the mathematics. But the general acceptance is you have two states that are superimposed in the single most building block of quantum information, that is a qubit. Okay? And as opposed to a classical bit. In a classical bit, you either have a 0 or a 1 as a storage. Then in qubit, you have something called as here, there is something called as block sphere. In a complex domain, you have a unit sphere because there is one axis 0 and one another axis 1. So all states of 0 and 1 superimposed lie on the surface of this sphere. Okay, so that is how it is mathematically represented. The analogy is like that. Okay. Some of the important things about quantum computing. Quantum computing measurement itself is inherently probabilistic, and the reason lies in quantum physics. So I will touch base with quantum physics, some of the principles, but you let me know if you want to go there, because quantum physics is governed by some of the very fascinating laws. Of course, it is a topic of interest for me. Heisenberg's uncertainty principle, for example. Right? So when we talk about superposition, it is also very important phenomenon which comes from again these basic postulates in quantum theory. So the wave-particle duality of the nature of systems of particles at the atomic scales was studied in parallel during the era of Einstein by several scientists like Niels Bohr, then Heisenberg, and several others, Dirac, Paul and Dirac, etc. So some scientists gave the wave equation, etc. So, but I think everyone must know some of the basics of quantum physics in order to move towards quantum computing, at least at some fundamental. Okay, so you have something called as nature of a particular particle. Let's say I have grains of let's say some grain. Let's say गेहूं का दाना लीजिए, मोहरी का दाना, ajwain, whatever. And if you have lot of such particles, if I bombard them, okay, let's assume that there is a hole. Let's forget electrons from here. Okay. So if I have only one slit, okay, or I have only one small hole, let's just say, if I pass on something which is like a particle, okay, if I take छोटे से अजवाइन या कुछ बहुत सारे if I throw them through the slit, okay, there will be a specific distribution here, which will be there is a screen. And it will be somewhere like it will be spread like this, okay, with a peak here and slowly decreasing away from the mean. It will form a Gaussian pattern, right? So this is something which is the particle behavior of subatomic systems. So if something is like a particle, if I am throwing it from a small hole or a slit, I am bombarding it continuously, multiple particles. Okay, it should ideally behave like a particle. The particle behavior means that it will. This is the parallel line, exact parallel line to this slit at the center of it, and then in both these dimensions, there will be more particles here, and there will be lesser particles here, like this, and the distribution will be Gaussian, like this, right? There will be more number of particles towards the center, and it will slowly fade out, mostly given by normal distribution, central limit theorem, we know, right? So based on that, if we bombard continuously infinite number of particles, it will be a perfectly normal distribution, correct? Now, if I put this complete thing in a water, let's assume that it is water, okay, and I put a table here. So what I was saying is that if there is a beam of continuous beam of particles, forget about electrons as of now, it will follow and it will pass it through a single slit as of now, only a single slit. Then it will form a Gaussian distribution here, basically spread out towards the line which is parallel to this. If these are two ones, we will have two peaks Gaussian. That is particle nature typically, but it will be Gaussian. Okay. Now, if I put this whole system in water, because we understand water waves better than other waves, right? So, if I put a small stone in water, how does it behave? From that stone, radially outwards, you will see something called as a wave. The nature of wave is given by wave equation. Okay, mathematically you can have that partial differential equation or differential equation, which will tell you about that energy getting transferred from the transverse wave or whatever whichever longitude in the wave. But this is now let's say transverse, but it is passing through this slit, and the other side of the hardwood, here again it is water. If you record the impedance somehow on a screen, you will get wave nature, right? So crest and trough. If there are two slits, you will get an interference pattern of two waves. Or even if there is a single wave, if there are two slits, it will pass on from here like this and from here like this, and then there will be intersection points, and accordingly based on the distribution of the energy, okay, there will be crests and troughs, and accordingly it will be distributed. There will be a very beautiful interference pattern here, which will be somewhat like this, high and low, high and low, right? So we know mathematically, behaviorally, how particles behave and how waves behave. Okay. Now, when some of the 20th century, early 20th century physicists were studying atomic systems, they started bombarding cathode rays of electrons eventually through this. So, ideally, if electron is a particle, okay, it should behave like particles, right? The distribution here should be Gaussian like this, faintly spread out distribution. If it is true, but eventually what they thought is that instead of passing on a beam of electrons, I will just pass on a single electron. This is where things get very interesting. So if I have a single electron, only one electron, I knock off one electron from an atom and I just pass it on through single or double slit, ideally not single, double slit. If you pass a single electron from the two slits, what is Young's double slit experiment, okay, what should happen? Electron should either go from one slit or the other slit, right? Or it will go from both the slits. The results were very fascinating, and this is very crucial in understanding quantum mechanics systems, because when they observed an interference pattern here, even you pass on a single electron, okay, it behaves like a wave. So how is this possible? Which means that electron is not a particle rotating or revolving around the center of the atom. It has a different property, it has wave-like behavior, and the wave equation for electron or subatomic particles or any quantum mechanical systems typically is given by something called as a probability wave. So it is given by something called as a wave of probability. What does this mean? It means that the Heisenberg's uncertainty principle says that you cannot 100% predict the position and momentum of a particle with 100% accuracy. So the product of the probabilities of position and momentum is always strictly less than equal to something of that is Heisenberg's uncertainty principle. But from an analogy perspective, if you want to understand it, it basically talks about if you know the exact position of the electron, you will not be able to know its momentum. So you will not be able to calculate these things. Again, a particular particle can have both natures, wave as well as quantum. So as a result, electron is traveling as a wave of probability of occurrence. So you can't say that electron is here or here or there. It will travel as a probability wave, and eventually that whole wave function gets implemented here. Unless and until you measure, you will not know whether it is going to interact. So there are certain fundamental postulates like these. So because of this uncertainty principle, superposition of states is something which is a nature. So if we talk about the state space of a single electron, it will be given by this probability wave function. Now this is a very crucial thing, because now this is something which is never seen in our real world examples. So superposition, uncertainty, and then there is one more thing called entanglement. So entanglement is another interesting phenomenon, which is where two particles can be entangled, and or these quantum states can be entangled, and they have no effect of space-time on them. So this is something which was very weird and was called as spooky action at a distance by Albert Einstein. And throughout his life, he actually opposed this particular thing. He never accepted it, but again, there are multiple papers, such as ER versus EPR paradox, Einstein-Rosen bridge, based on which the wormhole and other things have been recently discovered. Google published a paper recently, so it was about the ER and EPR paradox. And they said that one qubit is more or less like a bomb or an but these are all fascinating things. But from a usefulness perspective, entanglement, superposition, and interference. Okay, these are some of the major properties that we must know in order to understand the nature of quantum mechanical systems. So that is what we use to simulate information storage, okay, and computations on a quantum mechanical system. Now let's go back to our slide. So Young's double slit experiment is very crucial in understanding okay. So that is what goes behind creating a qubit. That is what quantum hardware manufacturers across the world are doing. What they do is they study some of the quantum mechanical properties. So the way matter at subatomic scale interacts with light, okay, based on those interactions, the way some molecules are getting created, based on all these things, there are various different families of quantum hardware systems which are mentioned here. So people thought that superconductors, if they are cooled enough, you can get stable quantum mechanical systems. So those hardwares which are based on the superconducting qubits, where the superconducting related principles are used to develop qubits, is the superconducting qubit hardware, which IBM, Google, all big players are this type of technology. Then there are very few players who are actually working on analog computers. Again, analog computers are not having very good precision, and repetition of the same experiment will not give you the same result. Again, that exists with a lot of other quantum mechanical systems. Then quantum annealing is D-wave, then photonic is Xanadu and some other players as well. Trap time, INQ is one of the major players here. Neutral atom is another way. And again, this is something, it's not my expertise. This is where the quantum hardware scientists have the understanding of. So, I understand the underlying quantum physics and the associated mathematics that we need to understand for executing software programs or writing algorithms. Okay, but there is a whole branch of developing these type of systems. Okay, where we have to study about the fidelity. So fidelity is something which is more or less like the robustness of a quantum classical computing system. You can say that fidelity is something which is similar to reliability of a quantum computer. Where you can rely on the results of a quantum computer or not. So if you have achieved better fidelity as compared to the earlier methods, then immediately people are publishing papers on that. Okay, so in the research community, you will find a lot of these things. If somebody found out that, hey, I can improve the fidelity rate of a quantum computer, or this algorithm is giving me a better fidelity for this type of quantum hardware and this type of circuit, then that is what is the research community is doing, mostly on the algorithm side. Okay, so again here, to some extent, exponential algorithmic time complexity reduced to linear. Basically, what it is trying to say is that if you have one qubit and one bit, okay, typically from the measurement point of view, there is not much of a difference. Although there will be superposition of zeros and ones in a single qubit, but if once you do the measurement, it is not giving you much of a quantum advantage or a speed up. But if you have 2 qubits, if you have 4 qubits, if you have 8 qubits, eventually you can store 2n states in superposition in a multi-qubit system. So that's why larger number of qubits can actually lead to some computations that are not possible using any supercomputer in the world. And that limit is somewhere around 32 to 35 qubits. Because 2 raised to 32, beyond that it is not possible those many states to be stored and calculated on any supercomputer in this way. So the moment you go beyond 50 qubits, it is something which is still useful. But we should find out a problem for which a 50 qubit system will be giving us some result that is non-solvable on a classical supercomputer or a high-end GPU based device also cannot solve that. But we need to figure out that problem. Now, IBM had 127 qubit system earlier, then they have recent one which is 433 qubit system. So eventually the number of qubits are increasing, but the more number of qubits you start adding, the noise in the quantum system starts increasing. So these are again problems which I am sharing from the quantum hardware scientist's point of view. I don't have the answer, people are working on that. But that is a domain where a software scientist will restrict themselves. For example, I know that there are issues in the current generation of quantum computing hardware, and which has huge amount of noise in it. So you cannot be certain on the output, and that's why you run it multiple times. So every quantum program that you will run it either 1024 times or 2048 times. And then we will plot the distribution and we will say that this is what our program is predicting. Okay, but the moment it will go to, let's say, 1000 qubit system, 10,000, 1 million qubit system, real applications of the same old algorithms will start happening. It is similar to something that people knew neural networks in 1970s or so, right? But they were not in practice because we were not having that much data and the processing power for that. With the web advent of the World Wide Web, and when internet data and businesses and all big dollar companies started showing interest into that, at that time people were having both the money, the infrastructure to develop neural networks. Okay, earlier people used to say that no, 3-layer neural network can approximate any function, you don't need multiple layers. The whole branch has emerged as deep neural network, right? Deep learning. Which people earlier thought that no, theoretically you don't need deeper neural networks, it is of no use. That's what was some of the thoughts in earlier decades. But eventually we have been discovering multiple ways and means that prove the earlier assumptions to be wrong. So now these are the different methods that are used across the world, and these are increasing day by day. So this is something which is blurred, but let's focus on this. These are some of the major families of concepts based on which, yes.
I have a question. Sorry to interrupt.
Yeah.
It's been playing in my head. Talking about Heisenberg's uncertainty principle that we can't figure out the momentum and velocity of particles at the same time, right? So, and then we also talked about quantum entanglement, where I think if I remember correctly, the concept is two particles imitate each other, right? They have the same properties. So
they are entangled to each other, means either they have the same or the flipped states, but
right.
they are somehow related to
each other, right? So by that concept, it's just me thinking out loud. If you measure the two particles at the same time that are entangled, and you measure the position with one, wouldn't you also get the velocity? Like, would you time the...
No, so when we are talking about entanglement of particles, so the concept of quantum entanglement in physics, okay, and the concept we are using for qubits, I am separating here the two things because this is a question for quantum physicists. Okay, so when we say that one particle, for example, typically the example is given based on electron spins. So electrons have some spin, right? So like clockwise and up, down, or clockwise, anti-clockwise, whatever you call it. So but essentially it is two states. Two states, it can have either one of the two states, right? So if two electrons are entangled, okay, they can be entangled in two ways. Like if this is clockwise, this will also be clockwise, or if this is clockwise, this is anti-clockwise. So the rule will be established. For example, while entanglement, I know that this is like if electron A is clockwise spin, then electron B is also will have a clockwise spin. Okay, but I am not measuring it right now. I am not looking into what is the spin right now. What I am doing is that I am taking this electron and I am going and putting it in some other galaxy, Andromeda galaxy. Okay, so it is separated by space-time. Okay, so Einstein's special relativity or even extension general theory tells that nothing can travel faster than the speed of light. Even information cannot travel faster than the speed of light. But quantum entanglement is a principle in quantum mechanics that violates this law, and that's why Einstein was very worried. So now if I don't know the spin of both of these electrons, but it takes I think several light years for information to come from Andromeda to here. Okay, but if I measure the spin or observe the spin of this electron A, instantaneously I know that what will be the spin of that electron. That is the paradox. That is the issue.
But also, the thing is, so that means the momentum of the two also potentially would be the same, correct?
Means Heisenberg uncertainty principle is different thing. Heisenberg uncertainty principle talks about the position and momentum of a single particle. Okay. So now, how is it coupled with entanglement is something I don't know. It's a quantum physics.
I was just thinking out.
No, now if you want to think it from a computer scientist perspective, then here is how we think. I will assume the states of these two electrons. Okay, if it is clockwise spin and anti-clockwise spin, I assume it is a 0 or a 1. Okay, whatever system I use to simulate my qubit. Okay, if the electrons are entangled, similarly I will call it as the qubits are entangled. So if two qubits are entangled, I can physically separate the two qubits. That is a theoretical analogy. People have done that, some Chinese scientists have done that. And they have proved that one electron was here and one laser beam and then they passed on the other one, right? So in some space, and then they measure the spin of the electron on the earth and they were able to immediately find out, yes, I know this spin, and somehow they have proved this quantum entanglement. So from a quantum computing perspective, we should think more about the entanglement of qubits. And I am least concerned now which underlying quantum mechanical phenomena is used for simulating this qubit. Okay. Then it becomes more or less like a mathematical representation for it. So that is a boundary typically a software scientist will draw. So these are the different methods of developing quantum computing hardware. Diabatic or annealing based methods, and there are sub methods. These are different ways in which this type of quantum computing hardware can be developed. Similarly, you have topological, then you have superconducting, trapped ion, photonic, spin quantum dot, neutral atom, and NV diamond. Again, I don't know each and every one of this, but there are different players, different quantum physicists and engineers who think that they can develop a quantum computer based on this particular principle or this particular method. They are manufacturing their own quantum computer. Then there are some other group of scientists in the world who think that, okay, this is my method related to NV diamond, which will be definitely very useful in developing a noiseless quantum computer which will be scalable, and they are this is how multiple research groups are. Nobody knows which of these methods will be better than another one. So each one of them has its own advantages and disadvantages or problems to deal with. Okay. But from a software perspective, we have some understanding. We should have some understanding about what is my underlying hardware, because in quantum mechanics you need to have an understanding about the underlying hardware to develop even algorithms. Because we will see further is that this concept of a qubit, you have a representation of a qubit in a mathematical notation. So we will need linear algebra for that. And then typically the state space state space is nothing but the representation of all states a particular information storage unit occupies. So if I have a single bit, I can represent it as a 2 by 1 matrix, okay, columnar matrix, where I have the 0 state and 1 state. Okay, there are 2 states, right? State 0 and state 1, and I can then put a Boolean value on that, whether state 0 is 0 or state, that is the, I will come to that. I will show you how you represent it mathematically, a qubit, then 2 qubit system, 4 qubit system, 8 qubit system. So based on linear algebra, and unless and until we understand that, we will not be able to understand what to do with that qubit, because qubit is a storage of information. So you store your data on a qubit. Okay. Then further to that, you will have multiple qubits used to store data. Okay. Then you will do some operations on that data. So which means that you need a mathematical representation of a single qubit, multi-qubit systems, and then operations on those qubits. So typically when we talk about qubits, we talk about their state space. Okay, because every qubit has 0 or 1 state. Okay, we are not talking about superposition, because the moment we measure, it will either go to 0 or 1. Okay, so there will be certain calculations that are performed in the superposition state that will be in the quantum domain, that because of the inherent parallelism inside a quantum circuit. But quantum computing algorithm to develop it is basically, quantum computing algorithm is nothing but a couple of circuits, input, so multiple qubits, circuits and operations on those qubits, and then measurement gate to get them back into a classical domain. So that whole analogy is basically a quantum algorithm. And when you attach it to classical data, then it becomes a quantum computing software program. So to understand from this level to go to a useful software program level, we have everything weaved out together. It's not something which I have discovered. It is IBM has given huge amount of material on this. So there are players now. These are the players across the world. Again, this is very old, but these are number of qubits. Now this is 5,000 plus actually here, and here this is this axis is underlying technology, industrialization, maturity. So who is having better applications as compared to others and all. But there are, you will find several such diagrams. Okay? So what typically this is talking about is these people, they are having less number of qubits related to quantum hardware. Maximum number of qubits actually Indian level. This is a company who has 5,000 plus qubit systems currently existing, rolled out for market use. Then this is still false here. It has less number of qubits are still less. And then the industry maturity is like this from here to here. Again, everybody is developing and getting advanced more and more. IonQ is also playing a big thing. So there are multiple players like this. This is a French company. This is again multiple players. But to demonstrate that based on these technologies, these are some of the known players who are developing their quantum computers based on whatever is their main analogy. And this is the quantum hardware variants. Some of them I have written: negative quantum, atom computing, so and today we have most of the players who are exposing quantum hardware for free. Several of them are exposing it for free because everyone wants people to use it and experiment stuff with it. And IBM is very ahead in the game. Now Amazon, multiple players are coming up, Google. So, for example, here.
Excuse me, sir.
Yeah.
I have a very basic.
Think of what property of superconductor which is giving me stable result. It will give me stable result at very low temperature. That's why that Google computer is kept at minus so degree Kelvin to
keep it stable. Okay, so that property is used to simulate one qubit, or some group of properties is used to get that behavior of the qubit. So you can then store information, and then the next problem is to scale it up. It's not only one qubit, no? So how we will convert it into multi-qubit system, then becomes an engineering problem. Similarly, you have something called as trapped ions. So this is again some material science related concept, that how can you use ions trapped inside a barrier potential or something of that sort. Again, I am not an expert into this, but it is something related to that. Similarly, some advanced materials like diamonds have some specific properties which they are trying to use. Okay, so that's why I said that it is very important for us to understand mechanical engineering based analog computers. Because we see these systems, mechanical system, fan is moving. So can I use this fan to do some calculation? Okay, this is still analog. Okay, so and analog is a continuous domain. The input that will go inside such a calculating machine will not be discrete inputs. These will be continuous inputs, because the system you are using is having the state space which is a continuous variable, not a discrete variable. Right? If you will use abacus for small children, it is a digitized version of a mechanical device. So abacus, if I use to store 1, 2, 3, and if I do calculation, okay, 2 plus 3, 4 plus 9, using abacus, okay, then it is a mechanical engineering based or mechanical computing system which is digital in nature. It has discrete inputs. It does not have continuous inputs. So now, as a computer scientist, if we want to convert this into an analogy for our understanding, we are talking it as whether my input state space is of continuous nature. Is it a continuous variable, or is it a discrete inputs? It is a variable that acquires discrete states. So here again we are representing it from mathematics into discrete states only. But inherently in quantum domain it is actually a continuous variable, because it is the nature of the wave function of that particle. And wave function is continuous. Electron, when we saw it going through two slits, it behaved as if it is a single wave that of probability that is going on. So you cannot say that this is where the electron is or that is where the electron is. So the whole behavior was like a wave. So now, based on multiple mechanisms, these people are using. So this is annealing is something related to some minimization of some energy of the system, and that is used to do calculations.
So these are the various types of quantum computers we can
yes,
based on either trapped on or based
correct.
on this, right?
So a quantum dot or neutral. And then this is a huge deep area of research which the respective quantum physicists, quantum hardware scientists, quantum engineers, they are using to understand which phenomena. Then in your experimental laboratories you study the interaction of photons with the material, like let's say some molecule, and you observe that okay, this property now can be used to store information as a qubit. Then how can this be converted into a computer or a machine that will not only store information as a single qubit, but as multiple qubits, then perform operations on those qubits. So now we are moving from not only the concept of quantum physics getting used to simulate a qubit, but now I am stepping into something where we are talking about engineering it into a useful large-scale multi-qubit quantum computing hardware. But even moving to that level, we will need two things. One is we will need these quantum computing hardware engineers who can fabricate these systems like a chip or some mechanism. We don't know how they do it. We know from our concept of very large-scale integration that there is something like a chip. And because Zanardo I have used, they had some 200 plus qubit system using photonic quantum computing device. They called it Borealis was the name of that device, which was decommissioned on 2nd June. But now they are converting an 8 qubit photonic system into a small chip. So why are they doing that? Because now they want to manufacture it. Na? It was a large interferometer which they maintained for quite a while, 1 year, for giving us a 200 plus qubit system using photonic laser interferometer device, and their phases and etc. they are used to do calculations. Okay, and but this is not scalable. You can't have now. I have interferometer. I will just continue expanding the interferometer using the different lasers. It is very difficult to maintain such a system. It is not scalable. So it is also an engineering problem for the hardware manufacturers to make it scalable. So the concept of chip definitely comes into picture, that can we scale this out for large number of qubits is another problem statement. But these are problem domains with the respective hardware OEMs or quantum engineers who are developing. From software, again, this is LV diagram, these are some of the applications that are basically analogy. This is like based on the lowest energy state they calculate, etc. etc. Some ways, and this is taken from NASA PPT basically some 3 years back. So that's why we can rely on that. This information is very clear. But eventually, to come into your answer is that now, if we are talking about converting this 1 qubit, 2 qubit, multi-qubit system, we need to have mathematics in place, right, in order to understand how we store information into these qubits. So then that is an area which we need to understand before moving into what is a quantum circuit. Then yes. The software is yes. Software will change, no? Because the whole gates. So the way you were having electronics gates and all semiconductors and diodes, that representation, it is different here. Storage itself is different. Yes, correct. Get different. So the state space of because 8 qubit system is not same to 8 bit system. Okay, you will get 2:8 states stored in a 8 qubit system. So that will come definitely. And then there are operators. The way we have operators like NAND, then NOR, XOR, okay, NOT operator, okay, and for addition, subtraction, etc. We develop digital electronics, and then for addition, subtraction, multiplication, we use it internally. Now today we have frameworks where we don't have to go back and do that assembly level programming and enter the gates. But I think during my bachelor's, I studied it in computer science, where we had these concepts where we use multiple gates to develop a counter or right. Even today in digital electronics laboratories, in your college this must be taught, right? So in a similar fashion, we will have to come up with a framework which will use this concept of a qubit, okay, convert it into a mathematical analogy, okay, use the respective mathematics, and thanks to Hilbert, so the state space of quantum mechanical systems is the Hilbert space, which is inner product space. So any vector space with a well-defined inner product is a Hilbert space. And so we use that analogy, and then we have something called as mathematics for quantum computing. So unless and until we understand that mathematics, which is based on Hilbert space, then linear algebra operating on that Hilbert space, the representation of single qubit, 2 qubit, 4 qubit, 8 qubit systems, then multiple operators. These are like linear algebra operators, right? If I am able to represent my data in the state space, which is stored on a single or multi-qubit system, then I need operations on that. So then there are operations related to qubits, okay, which perform those operations. These operators are based on the gates provided by quantum mechanics. And then we will study that we have single qubit gate, 2 qubit gate, 3 qubit gate, multi-qubit gate. So then we have the framework to devise the circuits called as quantum circuits. So usually using superconducting qubits using IBM hardware, I will demonstrate you during our hands-on lab that we can develop circuits. But even before going to a circuit of a level, just as we used to do it like a counter is implemented, but inherently what it is basically a complex structure where multiple gates, multiple NAND gates I can use to develop a counter, right? Or I can use it for addition, subtraction, etc. But it boils down to again Boolean algebra and basic mathematics. In a similar fashion, we will study linear algebra based mathematics which talks about the language to develop quantum circuit. And then there are certain potential advantages of quantum circuits which we do not get in classical circuits. For example, quantum circuits, you will get an advantage to do calculation in the Fourier domain. Because of some of the properties like superposition and all, you get a basic advantage in calculating something like Fourier synthesis, which is the basis of Shor's algorithm, which is the threat to the world. If we get a Bernstein qubit computer, the same algorithm will do prime factorization in seconds. So this advantage, which is there present in the inherent nature of quantum mechanical systems, we can understand by understanding quantum circuits, and then the nature of quantum circuits, and representing them into single qubit, multi-qubit, okay, and then having multiple operators on them. And then you come to then the place where that if I have a single qubit, 2 qubit, 3 qubit, then there is a problem where I have to then pass on data to this circuit. Then data goes through my circuit, what is happening at each level, so that transformation is happening, and then I have a measurement gate, I get the output. That is a computer program, quantum computer program. That is called a quantum program. That's it. So this is what quantum computing is about. Then it becomes more and more complex when we go to usage of software frameworks. So IBM will show us that how you can then use. People have developed software frameworks. You can use PyTorch, or you can use Python language for basic circuitry to develop it. Then a single gate I have to pass it on to, let's say, 100 qubits simultaneously. You can put it inside a for loop, and then you can develop complex circuit. You can develop something called a quantum Fourier transform algorithm. So then quantum FFT, the usage of quantum FFT, like prime factorization of integers. So today the usage of quantum computers is much more into solving these theoretical or academic problems like prime integer factorization, searching the state space inside a graph, so which is Grover's algorithm. So then these are some of the fundamental algorithms that we will move as the next level. So once we understand mathematics, linear algebra for quantum computing systems, starting from bits. So then we did not have to know about how these things work. Now I will start from here. The way you don't need to understand how Intel has implemented architectures against how Qualcomm is implementing it for mobiles or AMD is implementing. We don't care, right? I just write my Python program and there is an abstraction which takes care of it and we are done. In a similar fashion, if we understand the underlying mathematics and linear algebra for representing the states of multi-qubit systems and quantum circuits, then we can play with multiple operators defined, okay, based on linear algebra equals based on the data and the complex circuitry, and then we will develop different types of algorithms. Each algorithm is targeted to solve something, okay, and eventually then these algorithms combined or modified further will give us the practical implications or practical usage of the quantum program for a particular business problem or an academic problem of interest.
Sir, one more question.
Yeah.
Sir, we are saying that quantum circuits are having advantage that they can operate in Fourier domain.
Better
When we use frequency, we are talking about the frequency component. So here, how will we measure the frequency basically? It's a qubits frequency or
No,
which frequency?
frequency of the data. You are passing on the input data, right? If I want to calculate, do the Fourier synthesis of an input signal, okay, I want to calculate how many inputs, different signals are contributed. Frequency normal Fourier analysis I am talking about. But in classical, so there is some inherent nature in which we get that advantage. So, for example, performance advantage. It performs better as compared to the way we program Fourier analysis in classical.
It's faster.
Faster. Correct. So, yeah, correct. So, faster, yeah. So, performance wise. So, most of the people in past 2 decades focused on getting quantum algorithms that are performing in terms of speed, okay, better than the respective classical algorithmic counterparts. Okay, that has been the direction of research for quantum. That has been the direction of research for quantum algorithm scientists. But in previous some years, several people are now talking about that quantum machine learning is not only about getting better speed. There are certain problem classes or problem domains that are unsolvable in the classical domain, especially related to photonics. So some, and again these might be different for different things. For example, RAIT-ACM computers are better in simulating the underlying behavior of quantum mechanical systems. So if you want to study the properties of quantum, the material, the quantum mechanical properties of the material, to understand that how it performs at a micro scale, it can be used for drug discovery. It can be used to develop new molecules, new materials. So materials development has been the first area of application of quantum mechanics, even from the business point of view. So developing better and newer drugs is easier maybe using quantum mechanical systems. And then again, out of these, some are having a better advantage in getting the quantum material simulation related applications. Again, that is again an area of research. We have to still discover. For example, RAIT-ACM has been proven to be better in providing applications related to drug discovery. That doesn't mean we cannot do applications using other ones, but again it is a potential area of research. But people have identified certain problem domains for which no particular type of hardware and then set of quantum algorithms are better than the classical counterparts. Or you can never get a solution using classical computer, but you can do that only using quantum. That is a real challenge. If we discover that kind of problem, then that is a real breakthrough.
So, then whatever linear algebra operations we will be performing on qubits, so it will depend upon the type of the material also, right? Or it will be same?
No, it is a mathematical framework to represent
the operation means interaction, some interaction between that will be taking place. So it will depend upon the material where the actual process is taking place.
No,
for example, it is photonic or RAIT-ACM.
Correct, but we are simulating those processes. We are using those processes to simulate something called as a qubit.
Yes, we are using this, like as you said, that
this
qubit
to
is in the
develop
form of
this.
this, either one of these, right? Now we are performing some operations on qubits.
Correct. So
because we have to develop some qubit circuits.
That is mathematics based. No? Then that is mathematics based operations. It is a mathematics problem.
So it is not basically dependent on.
No, it is depending on this, but that is an abstraction for me. How my qubit behavior I get from which technology? I am not clear. I don't care, but I know how to represent this qubit mathematically.
So now onwards,
I have a mathematical language or framework to describe the fundamental building block of information storage and processing in a quantum computer or a quantum mechanics based system. Right? So that's why this is again from a computer scientist perspective I am talking about. If you go to these days, they will talk a lot about how they face problems in simulating that. And again, there are.
It's like that candidate will behave like candidate irrespective of which material.
Yes, because that is the formal language of computation that we have formulated for qubit. If I am talking about qubit, I have a mathematics to represent this particular stuff. Yeah. How these states, infinitely many states can be represented? I know the mathematics, we have devised the mathematical framework. Again, there are certain families of algorithms that I have recently discovered which fall into this category, for which you will not get a straightforward answer to this question, but I will keep that aside. But you are correct, there are certain methods which will be very much coupled with the underlying hardware. I agree, they are similar to an analog computer, right? There are methods, but we are moving towards manufacturing it, so we need to come up with a formal language, because there are certain manufacturers who also claim that we can simultaneously superimpose 4 states. It is called as qubit. So if 4 states I put inside it, okay, so it will be 4 raised to n, or I need to calculate that how it will be, the state space will exponentially increase. So it will be much faster, speeder as compared to the way you are representing fundamental information as a qubit. We are keeping that apart today. Okay, it is something like where the fundamental block of storage has been changed, but and what will change eventually is the underlying mathematics will change. That's it. But it is just changing some of the ways and means to formulate this problem in linear algebra. That's it. But there are certain behavioral properties of quantum mechanical systems which they contribute to the quantum computation or information processing. Then definitely I agree that it will be different. But again, it's not easy to understand, because we have to understand that particular system also. Physics behind that system. So there are certain algorithms I can name which I know today, but why it is different from these, I will not be able to answer directly. There might be some question. For example, Zananu, I asked this question to Zananu a couple of months back. They were also unable to answer. Something might be proprietary, or there might be certain things which they themselves might have done a lot of research, and some hardware scientists might answer that question. But again, you are correct. What you are asking is correct, but for our general usage perspective, we have an established framework.
Excuse me, sir.
Yes.
Sir, is there any architecture for quantum computer?
Architecture?
Any architecture?
So,
because for digital machine, we have like von Neumann and Harvard.
so von Neumann architecture and what you are talking about.
Yeah, but here it is architecture.
So, it's a good question, but von Neumann is mostly based on the classical.
Storage system is entirely different in quantum. So without architecture, how can we build an?
No. So each quantum computing hardware will have its own architecture. Each quantum computing hardware system will have their own specific architecture. That is the challenge here. And again, there are 2 things here: hardware architecture and computing architecture. The von Neumann you are talking about, computing architecture. So again, I don't have an answer. I will get back to you on this, but the analog of von Neumann architecture, which is a computing paradigm, okay, in quantum is something I think we will have to think. I don't know, because the fundamental unit has changed. Okay, so Turing machine, for example, Turing machine analogy is based on a continuous infinite stream of bits provided as an input to a machine called as Turing machine. It reads one at a time, right? That is a Turing machine analogy, which Alan Turing will take. But now, if you have input as a qubit, then how will you do that is something I don't know the answer frankly. Or today also, from a practical point of view, I will tell you, today also we don't have data in quantum. Okay, so there are 4 quadrants. Okay, I will come to that. These are the 4 quadrants. You have data as classical and algorithm also as classical algorithm and classical data that we have been using for past several decades. Classical computing algorithm on classical data. Then you have classical computing algorithm on quantum data. We don't know what is quantum data is impossible, because quantum data is, let's say I want to simulate an n-body system using classical supercomputer. We have been doing this. Okay, some of the chemical companies and pharmaceutical companies, huge supercomputer, but hardly 8 atom molecule or 6 atom molecule I will be able to formulate based on that. This is not very effective. Then we have classical data and quantum algorithm. This is the space where all our algorithms will belong. We will be playing on this space because all data we have today, this is a classical computer. Whatever I see is the classical data. My job is to transform that data into a quantum domain. Okay, so that first operation will be transferring my classical data inside a quantum computer. Then the quantum circuit starts playing. Then but then these no, I think if it is huge data, then definitely I don't know how to, but we don't have that big quantum computers today. You will not have an input of more than 100 or 200, 500. If it is D-Wave, then you can have a circuit which has, let's say, 1000 qubits. 1000 qubits in a single circuit, for example. But still, it is 1000 values you pass on, right? 1000 when 0101, 1000 values only you pass on. Again, you convert images, so that is where quantum machine learning. So then you have to pass it on multiple times. The way we do multiple passes in neural networks in a similar fashion, you have to do it. So yes, there are limitations. And the fourth one is this one, quantum data and quantum algorithm. So see, there are certain domains we still don't know, but we can still take inherently the advantage of, for example, ion. If I use a trapped ion for simulating a molecule, most probably I can get some data out of this which will be much better than a classical supercomputer. Something of that sort. Okay, so to answer your question, again, this is not computing architecture. Ideally, I am not talking about here at an architecture level, but we need to think on this. I have not given enough thought to this. So one human architecture for input. If it is not, it is a bit stream. Today, Turing machine, the input data is a bit stream. So we need to think. So this is it is this data. Classical data is getting passed on to Turing machine. That's what I think. And hardware architecture, for every quantum hardware, it is different. They have their own architecture. For example, photonic quantum computers are laser interferometers is one of the models that they have used. Okay, so then superconducting qubits, they put it in a superconductor and then they do some calculations based on that. They converted it into a multi-qubit system. Okay, and then that is how they expose it to us. And so that's why it's $1 billion job actually to manufacture a quantum. So that's why quantum hardware fundings, you will see it is millions of dollars. If you want to manufacture a quantum computer, it takes huge efforts. Software funding comparatively, it is, I would say, 0.01% or 0.1%. So the funding which we got from IT, it's all based on algorithms and software. But we have access to at least 5 different types of quantum hardware systems. So the advantage here is that I am analyzing which type of hardware will give me what kind of result for a particular problem set. No, not all. Superconducting I have used, photonic I have used, trapped I know, but I have not applied it to chemistry. I know I have attended some workshops for trapped ion and all. So these three I know for sure. And then there are a couple of them which I think on Amazon market they provide it, but we need to go do lots of hands-on on that. But it is very interesting. Yes, to learn it is a very great problem. Even quantum teleportation, based on the quantum entanglement phenomena, is demonstrated several years back by my videos as well. And then these are the disciplines, for example, machine learning, quantum information processing, quantum machine learning. At the intersection of these two. Then simulated annealing, classical domain with quantum deep sampling, then there is a interaction quantum annealing. Likewise, so there are multiple disciplines actually forming these interdisciplinary areas. Annealing Annealing is more or less related to finding out the low energy state of a quantum mechanical system. So inherently, any system, if you leave it, it will go towards its lowest energy state, right? Typically, any system will go to its lowest energy. This is a, and if I keep it like this, it will, like this if I keep, it will fall. But here it will get stable because there is a balance between the normal reaction and the gravity acting on this plane, etc. But nothing will stop at a higher energy state. If there is a cricket ball and if there is something like this, if I put it, it will come here and it is again, so it will go like this, but eventually it will stop to the lowest energy state. So any natural system, both in classical and quantum domains, usually tends to go to a lowest energy state. So they are using some quantum mechanical systems to simulate the qubits and then calculate it naturally. So simulated annealing is an algorithm where we heuristically move back and forth and calculate the optimal maximum or minimum function, right? So similarly, in quantum domain, they use some properties of quantum mechanical systems which naturally tend exponentially towards lower energy states. So if you use that system to encode data, it will naturally go and solve your problems. So there is particular class of problems called as BQP problems, okay, which I will come in the next slides, which are used to solve quantum problems using quantum annealing based supercomputers, and they convert other problems also into BQP domain, and they can't do some transformation, they convert it into BQP problem and then they solve it. Mostly optimization problems can be solved using quantum annealing. So this was the first application of quantum computer, and the first quantum computer operational was from D-Wave, which used quantum annealing. And they claim that this is the best way. We don't have to go the qubit route, but they after going 5,000 plus qubits, they have hit a benchmark. So it is not scalable beyond that again because of the noise or inherent noise increasing in the quantum system, etc. But there are other ways now based on superconductors. So in quantum annealing, there is something called as ocean software. They have a software called Ocean of D-Wave. They use for it, and then their own hardware is there. That E-Wave hardware is available on Amazon packet from past 1.5 to 2 years now. They have decommissioned. So what is happening that some of these startups, they develop their systems, give it for free to the public through Amazon cloud or some other cloud, and the moment they get all the insights, eventually they decommission their hardware from Amazon. This has been a trend. Same happened with Zanadu. So we are collaborating separately with Zanadu to get their hardware on now their hardware is only available on their own cloud. So they develop their own cloud computing service to expose their quantum hardware.
One more question, sir. Whether general purpose application can be executed on quantum?
General purpose means this integer factorization and these problems are predominantly solved. Okay, yes, this is definitely doable, but most of the players in the industry, BMW, Mercedes, aerospace companies, fintech giants, JP Morgan is publishing a lot of research in applications of quantum algorithms to predict or forecasting problems in finance or even quantum cryptography, etc. But real world applications, even if somebody finds it, it is proprietary because it is either business funded, or if it is government funded, it is mostly for aerospace defense or other applications. But still, for drug discovery, for certain things, it is a very open community. Because of the open source revolution in software, it is much more knowledge shared amongst everyone. Unless and until some breakthrough discovery is there, I don't think, and even if it is discovered, you don't have the hardware. Even let's say I know the best algorithm, I don't have the hardware, right? I have to go and get the hardware from someone who has developed it. And it is millions of dollars worth invested. So it is not a job of one or two, it is so many people are involved in it. And then there are, from business side, it is competitor game. If one player is investing, another one will go and with some other OEM and they will start doing things in parallel. That is how it happens. Classical computers will not fade away. No. It will be the next several decades will be hybrid quantum classical. The era of hybrid quantum classical algorithms and software. That is the next era. Till we get to a level where we have 1 million qubit system. Let's say 1 million qubits is 2 raised to 1 million. It's a very big number. Those many states you can compute or store. So that is a very big number. If somebody gives me 1 million qubit system, same algorithm, short algorithm, you run because you can have multiple input data passed on to it and it can break the RSA. RSA is what 2 raised to 256 states I just need to crack an RSA algorithm. That's it. So it will do everything in parallel. So in one shot it is possible for a quantum computer to break these keys. So these are some, again this is quantum, so computational complexity theory. This is what I was talking about. So there are some problems called as BQP complete. So you have NP versus P versus NP and then NP complete and then C-space problems. Again this goes to computational complexity theory and there is something called as BQP. I think this is bounded error quantum polynomial time complete. Again, I am not expert into this, but this is something which I know that this is a reference. So essentially you have to identify the class of the problem, where it belongs, and then map it to the respective method or algorithm that you want to devise to solve that problem. This is very so some major applications of quantum simulation, which is I explained already, quantum machine learning, optimization problems, and several other algorithms also. I have just mentioned some basic applications here. And these are all problem statements. This is a very important slide. So now let's consider that we will go into the details of quantum circuits. If we want to know that I have a quantum algorithm, for example, right? How to compare it with the existing classical counterpart. So this is an analogy for it, which the whole industry is using today. So do your algorithm beat some good classical methods? If the answer is no, then there is no point. Why are we developing that algorithm? Right? Let's go back, let's again find out which algorithm is going to beat the existing known good classical methods. For example, if I don't know that this algorithm is better than in quantum Fourier transform than the other known methods in classical, no point in applying that algorithm. It is still not going to perform better. So you have to develop an algorithm which is better than some good known classical methods. If the answer to this question is yes, we call this stage of the research as let's say we have achieved limited quantum speed. This is a terminology, quantum speed. You will find this terminology in research papers. So if we go into research paper, people will say that we have achieved this. Our method claims limited quantum speed over the 4 known classical algorithms used to implement quantum Fourier transform. That is a research paper. I am just telling you the conclusion of research paper. This is how the research community is progressing. Okay. If you beat all classical methods, this is a very important stage. If we achieve this level, I have discovered something or somebody has discovered, which most of the players are moving towards this direction. If it is yes, then it is called as we have achieved quantum advantage. So which means that I know a method in quantum computing that no other classical supercomputing or computing or any hybrid classical system is better than that method. I know a method which is much better than the existing all known classical methods. Then we call it, we have achieved quantum advantage. Again, you will find this word in research-based publications everywhere, IEEE, Nature, you can see the journals. Now, even if we are at this stage, you will say, okay, great, so what else we need to do? So the issue is that the millions of dollars that have been invested in development of the method or algorithm and the underlying effort in building that particular quantum computing hardware, the overall package, software plus hardware plus method, if it is not worth it, then there is again no point. For example, if I am not getting enough speed up, I am getting somewhere here, even not quadratic speed up, a very limited speed up I am getting as compared to the another classical counterpart, then there is no point in doing that unless and until I have a big problem. For example, I have $1 million problem to solve, or some company has $1 billion worth problem which has huge data and that method is going to solve that problem, then it makes sense. But if it is not the case, then again there is no point. But if your performance is so much better that it would be crazy to do it without a quantum computer. So that stage is called as quantum supremacy. So if the question, answer to this question is yes, then congrats, you will achieve something called as quantum supremacy. This is again you will find in papers, quantum supremacy, only very few people have claimed. Google published a paper claiming first that we have achieved quantum supremacy. Okay, and that is a big word today, buzzword in the industry, that somebody has achieved quantum supremacy. Xanadu claimed in 2021 using their photonic quantum computing hardware a quantum advantage. So likewise, there is a competition going on in the industry as well as academia that we are better. But if you ask me about industry is crazy. They are actually looking for this thing or this thing. Okay, but in academic research, you will still find that this is also big distance. So these are 3 stages to this. If someone reaches here, it is still a great achievement. But the industry won't be interested in it. For example, if somebody, one of the faculties in this group, let's say, discovers a great algorithm to solve some problem, but it is not going to add a value to solve a real world business problem because of whatever can be the reason. Because we have only 100 qubit system available, we don't have the hardware available. So we will have to wait for the next 5 years to get that hardware available. Likewise. So it is still not useful for the business. So if you go and actually, I am talking corporate versus academia here. So in the corporate, you will still see that to make the business interested is a different ballgame, and to make the government interested is a different ballgame. But ultimately, from a research point of view, these are the 3 milestones that every researcher in quantum computing needs to focus on to get further into quantum computing research. So again, I think I talked about all these things, but I will just keep the slides for a couple of minutes for all of you to go through. Again, this is simple, basically taken from Wikipedia. You can get all the definitions in Wikipedia. The standard definitions people have also published in research papers. When first time somebody talked about the concept, it has gone into some research papers, and then it came to Wikipedia. So now, from a research point of view, every analogy related to classical computing, you will have to correspondingly form a similar analogy in the quantum energy. For example, you have computational complexity theory in classical domain, like what sir was asking. So similarly, for quantum complexity, the computing architecture related to computation, on human architecture, we will have to formulate similar analogy for the quantum computing. And people working in quantum information theory and all are, people go deeper into these things. Again, the most commonly used model of computation is quantum circuit model. That is what we will be studying, and there is a mathematical framework to understand that. There are certain other models for which we have different types of way to encode data, etc. Again, there are different ways in which we encode classical data into quantum data. There are 3 to 4 minimum ways in which you encode that data. It is similar to the multiplexing concept, for example, time division multiplexing, frequency division multiplexing used to FDPRAIT, right? Similar. This we have gone through already. So the quantum technology landscape, especially, I talked about some things, quantum networking. So quantum is one of the predominant technology in developing the 6G Wi-Fi that is coming up in picture. You will not find 6G architectures without quantum computing and artificial intelligence. Quantum machine learning will be a crucial part. There is an IEEE transactions paper that I will show you, which talks about the 6G technologies. So there are specific research groups working on only quantum networks, especially because this is going to contribute to quantum internet. So can you use quantum computing, quantum communication devices to build a quantum internet or quantum computing based internet? Similarly, quantum materials. Quantum materials is usage of quantum mechanics to develop new materials or even materials that have quantum, that have properties at that state in quantum mechanics. And quantum memories and quantum emitters and quantum chips. So developing quantum random access memories. Okay, from software side, quantum RAM is a paper to develop. So because random access memory is a mathematically represented concept also. Right? We have RAM as a basic architecture for classical computations. Because now we don't care, no? For all algorithms that exist today, we assume an infinite two-dimensional RAM, and based on that, then we optimize our algorithms. So whether it is Google search algorithm or not, it is based on that. So what sir was asking, right? So in a similar fashion, people are developing quantum memories, quantum repeaters. Repeater is more again related to communication between multiple systems. So this is not only restricted to quantum computing. Okay, so the bigger stack is called as quantum technologies. So using quantum hardware only for computational storage and information processing purposes is quantum computing, but there is a broader area called as quantum technologies, where similar to we have edge nodes, then hybrid systems, mesh computing architectures, fog architectures, right? Hybrid architectures, cloud systems, and edge systems connected with cloud. Okay, these are distributed systems where compute happens at different places. In a similar fashion, quantum technology is a broader landscape where you can have quantum networking, quantum simulators, these are again, this is post-quantum cryptography, again quantum software, quantum cloud computing, quantum key distribution, this is related. Then quantum sensors is an area which is not typically under quantum computing alone. Quantum sensors is like there are particular devices in quantum that can act as a miniaturized edge miniaturized edge devices. For example, there can be some quantum mechanical properties of a sensor or a transducer. So there is a mechanism of quantum sensing, quantum sensors or transducers, developing sensors and transducers based on the quantum mechanical properties of materials or systems. Then you can couple it to, let's say, satellite. If I put it on a satellite infrastructure, I can have that kind of data if it is better than the existing classical sensors or transducers, like this. So you can have gravity sensors, you can have some different electromagnetism related sensors. You don't know. So this is another area. Atomic clocks, particle accelerators. And multidisciplinary research in quantum computing typically goes into these many different areas.
Startups nowadays were actually in quantum computing. I came across one startup that is very so I just wanted to know, like, are they focusing on the quantum hardware or quantum software?
No, so different startups.
Want to see a quantum computer in India?
So what I know, but there are government initiatives. Obviously, people are working multiple groups. So there are two missions in government of India. One is the renewable energy mission of Modi government, and second one is the quantum computing mission. These are the two main funding related missions. Huge amount of funding is getting. The reason is we don't have awareness, right? So 7 years back when I started, even for my PhD, it was very difficult for me to find the expert in my research advisory committee. We hunted for people. So doing a PhD was like more or less forming a startup for me, because I was looking forward for people who have existing knowledge and who can evaluate the work. So there are very few people. Otherwise, people who have knowledge, they are not here in India. Even they are having Indian origins, they are not in India. Or if we have some people there, some people are more focused on academic research, etc. There are people. I am not saying that there are no people. But again, so for example, recently one lady from RRI, she has received good funding. So, that is on quantum communication. Okay, so they did some experiments using satellites and passed on quantum communication. They have did some experiments. So again, each and every field is of very much in-depth research. So we should have people who will continuously learn and acquire the knowledge, contribute, collaborate with multiple players. So I participated in online international symposiums with, like, for example, these are free. Google Symposium in 2021 or 2022 I participated. It was late midnight, I participated in those sessions. I get to know which are the people who are expert in a particular area across the globe. That is how we have to communicate. That is how we have to collaborate with people. But eventually, siloed research definitely is not going to help us in India. But again, it is not something which is we can do by just developing software systems. Because again, my focus area is that, but I am getting that software through Amazon Bracket funded by government of India. Okay, but eventually we don't have that much capable systems today. Or if they are existing, at least they are not exposed to them, and that is what is happening. At government level, every government will keep it confidential because it is a different ballgame. But at business level, it is mostly a matter of money. For example, you have to pay for that hardware. And again, if we want to develop those systems, if people are now, because Xanadu is now moving towards scaling out their established photonic quantum computing hardware. They are solving the next level problem. If some research group in India is developing a photonic quantum computing hardware, they are still at the 0th level point. We are still trying to figure out how we will simulate a qubit, and then how will we develop a circuit, and then we try to solve it for 8 qubit or 10 qubit. These guys, they develop some 200 plus qubits photonic interferometer. quantum computer. Then they exposed it to the world. They got all the insights on multiple algorithms and all, and then they knew that yes, this is doable. They then started solving the problem. Can this interferometer be miniaturized and converted into a chip? And recently I have seen Zanaru has successfully claimed that they have been successful in creating their 8-qubit exact devices fabricated inside the chip. So the whole interferometric device, which was let's say bigger one, now if it resides inside the chip, they have the first step to convert it into a scale-out infrastructure.
They would be going for
Then it will be very close to creating a 1,000 qubit, 1 million qubit system eventually, right? So, but again, the problem is not only about quantum physics; it is also about engineering. We need good engineers who can then fabricate. We don't have the hardware industry. No? The whole hardware industry is in Taiwan. The best hardware manufacturing happens in Taiwan today. So we don't have the state-of-the-art world-class facilities to fabricate technology inside small chips. So we don't have the know-how. And when software industry grew in 1980s, 90s, I think at that time also, we focused on software being a service-based industry. Eventually, we will definitely have a cutting edge in software. I am pretty sure about it. But on the hardware side, unless and until manufacturing gets outsourced to India, eventually we will be there also. I personally think that we will go there. But the research is not simple. The problem is not simple, it is a complicated problem. Because now let's talk about practical problems. There is something called as decoherence. So if a quantum system exists, I created a quantum system. Okay, it is not like I have created this laptop, I bought this let's say 3 years back, and it will stay as it is. I will be able to use it for next several years. Okay, any system, this machine, it is stable. Quantum computing hardware and computing systems are not stable. They move to a state called as decoherence, which is inherent nature of quantum systems. And again, there is in addition to quantum physics, entropy and all, whatever may be, energy dissipates. So you can't have stable systems in quantum computers. That is a major challenge. So people say that in superconductors, if we are able to maintain those low temperature continuously, they are stable. So now we can use it for a longer duration. But still, the computation happens in milliseconds, microseconds, but after some time it goes to decoherence. The phenomenon is known as decoherence. So to maintain it for a longer duration is a different problem, and that's why current generation quantum computing hardware systems are called as NISQ devices, which is noisy intermediate scale quantum computing devices, NISQ. So we are in an era where we have only NISQ devices at hand. So if I am an algorithm scientist, my domain is a quantum algorithm and quantum, I have to problem statement where we have to focus on the whatever device I have available today, can I still solve something that is very useful for the business. So then they talk a different language. They don't talk about only quantum supremacy and all. They talk about business usability of quantum computing systems. Because that is what they are interested in. If a businessman or an IBM or some company, some aerospace giant or some pharmaceutical companies investing $100 million, they will need return on investment. So that is a different problem. So again, each layer in this whole technology stack has their own ROI related problems or business technology related problems. But still, I would say the research is happening at an accelerated pace. So what people thought that it will take 4 decades, it is happening in 1 decade. That is because of the open source research, everybody is sharing the information, people are trying to find out the newer solutions, so it is happening at a very fast scale. So these are all the trends. For example, Continue, there is a company called Continue, which was earlier called as Cambridge Quantum, which has been bought by Honeywell. Honeywell bought Cambridge Quantum, and then They renamed it as Continuum, NUUL. So they have developed framework for quantum natural language processing. We don't have a hardware today, but we do have a software framework that can do quantum natural language processing. So if tomorrow the hardware comes, they will have a better edge on them because they are very advanced into that. They have the algorithms and software frameworks on them. So this is old architecture, but this is a software. So you were asking, sir, this is software architecture stack, hardware context from a software framework perspective for IBM QSP and IBM QXT. So again, the way we have compilers, we have operating systems, etc. We will find similar type of stack. Quantum hardware is here. We have QSP circuit library and core functionality. Using this library, we develop circuits, quantum circuits. Then you have some of these classical solvers, then imagine solvers, then Q-flow solvers. Second quadratic quantum unconstrained binary optimization, something like that. And then you have optimization algorithm. The algorithm is at this level. Then you run it on here. Again, there are certain things where you develop the quantum circuit, but internally while implementing it, you still have restrictions. So theoretically, we have all the gates which the library provides. But at a hardware level, they don't have those many gates implemented. So they convert some type of gate into some type of gate to make a particular gate that has been coded here. It is still at that level. We still have our programs at this level. And then you have this high level modeling language.
So next session we will be having at the topic.
After lunch we will. Solving optimization problems, developing high availability computing and storage systems, etc. Challenges. Large number of qubits are not there. Software needs a lot of work. No, but this was an earlier statement. Now today we have so many software frameworks that are existing. And then this is where I will stop. I think. So I will do some coding, but I will also give a glimpse of the underlying mathematics to understand the complicated problems. Any questions? Please let me know. After lunch we will come.